Let's get back, and now we have a chance to listen to Povilas' presentation. And Povilas is really like the guy who's been around for many projects on infrastructure. He's seen it all, and he's also the co-founder of Vienetas, a company that is both deploying, designing, and managing all kinds of infrastructure projects. And he will today share his experience on which challenges do we come up with running blockchain on AWS, and I'm really looking forward to that. I think it will be very interesting. Povilas?
Yeah, you didn't tell me, to tell only good things, right? So
I forgot.
Yeah, so that's a bit sad story. So hi everyone, my name is Povilas, and as Julius already mentioned, I usually run infrastructures for other people, and this talk is heavily influenced by that. And today I want to share a story about, we had a task to design a system, deploy and run it on AWS for one of our customers. And Graphene is a blockchain technology which allows you to build a permissioned networks. And we had a task to build a private chain, essentially, which is run by us. And you might ask why Graphene? Because there are so many options today, and it might be not so popular. It started getting popular maybe 2 years ago or so, and you might heard the names like BitShares or Steemit or EOS. EOS is all over the place nowadays, so Graphene is predecessor for that. And lots of code base is still shared between original Graphene and EOS, for example. So one of the main reasons why Graphene was chosen is the ability to have sustainable huge amount of transactions per second, and it's in thousands of transactions per second. And if you compare that with public networks like Bitcoin or Ethereum, so where it's a bit different story. And we've also seen, in Graphene's case, we've seen such numbers where people claim that they can do like 100K transactions per second, but I haven't seen that, and nowhere near that number, and probably that's more like theoretical limit. And people do like 10K transactions per second, but you need some fine-tuning to do. And on AWS, on moderate size instances, without any tuning, you can do like 2 to 3K easily, without doing anything. And another interesting feature is that a block is produced every 3 seconds in original Graphene, and in others, it's in BitShares, it's like 1.5 second, and EOS claims to do that every half a second. So, and in Bitcoin and Ethereum, it's completely different story, as we know. And also, it's another interesting feature is that it's a proof-of-stake system instead of being a proof-of-work. And Ethereum today and Bitcoin is proof-of-work systems. And it wasn't the main reason why we chose it, but it's kind of nice, right? Because in a proof-of-stake system, you essentially, vote with your money for the ability to produce blocks instead for simply burning your planet down. And yeah, so I'll be mentioning witness node and witness ID interchangeably in this talk. So witness node in the Graphene world is essentially it is a process which participates in the network and participates in the consensus mechanism. Exchanges the data, and it is a process in the container or running on your machine. And witness ID is the thing which it's the entity which is addressed by the in Graphene you don't have addresses per se, but you have this hierarchical naming convention, and this ID is tied to key pair. And you can have multiple witness IDs running on a single witness node, and you can have multiple witness nodes in the network. And these witness IDs are then used to produce and sign the blocks. And voting process I mentioned before is when you bootstrap a network or you join the public one. So if you create an account, you need to get some kind of stake. So if it's your own network, so you can create a stake and then transfer it. And then you create witness accounts and vote for them. So essentially you choose which IDs will be able to produce blocks in the network. And after that, you push that configuration into witness nodes, configs, restart them, and everything starts. And to give you a bit more of context, so that's how our typical reference architecture looks like. So I'm pretty sure you've seen this picture. It's very popular, and essentially, when customers ask us to deploy stuff in Amazon, it's usually it looks like this. So we use we try to use as much as possible, native Amazon services, especially at first, due to speed and simplicity. So usually we use, for example, Amazon ECS, ECR for Docker images, ILBs, ELBs, KMS and similar things. And here how it looks like, so high-level Graphene infrastructure overview. So it's a single VPC isolated one, also cluster span multiple availability zones. And we usually use ECS, and the first iteration of this infrastructure design was using ECS service. And we used NLB to route traffic to all of these nodes. And then we used SSM, which is Systems Manager, and in particular its parameter store feature, and KMS to store configuration data and encrypt sensitive data also. And also we used EFS service to persist the data. So it's NFS running underneath, we had pretty decent results with that. And usually we bootstrap all of the things with, in Amazon at least, using Terraform, and then bits and pieces of shell scripts and whatnot. And we usually, one thing is that it was a first warning sign, I would say, because when you go and check, the project, especially if it's unknown to you, usually check, how live it is, what kind of community is around, and the first warning sign was that there were no binaries produced and no Docker images. It wasn't a big deal for us because we built all of the images by ourselves, and there are multiple reasons, but I think these are pretty good rules to live by, and so you shouldn't run anything inside the Docker container as a root user, like never. And also, if you didn't audit images which are pulled from Docker Hub, you also shouldn't do that by default. And having this in mind, we built images from the source. And as we have automated pipelines, it wasn't a big deal, and we made sure that Graphene inside the container will run as an unprivileged user, not as a root one. And that's an issue because most of the images you pull from the Docker Hub, for example, they still run as a root user. And it might not be a big issue, but root user inside the container is the same as root on your host. And we've seen many privilege escalations and escapes from the images where you simply mount a directory as a volume to the container, and then you can escape by creating cron jobs, for example. And so you need to be aware of that. And another thing, we've been pretty cautious regarding accessing EC2 internal metadata endpoint. So usual practice is, I'm pretty sure everyone does that. So when you bootstrap your machines, usually by means of firewall rules or other means, you usually disable access to anyone except root user. And if you run default images, so that user is able to use your access this metadata endpoint. And then you can access, so if you attach any permissions to IAM machine policy, so then you can get temporary keys for allowing to do something, and you can then elevate privileges or do something else. And so when we had these images built, another challenge was to set up a peer discovery mechanism, because out of the box, Graphene doesn't support that. It doesn't have any. So it just expects that you put all of the peers into the configuration file, and you list all of them. So it's not enough to put your like bootstrap node or well-known endpoint. And if we take as an example Geth, which is Ethereum client implementation. So when you start that node, it automatically connects to the network, and you don't need to do anything. You can rewrite the default configuration by providing your own bootstrap nodes, but also it works out of the box, and it works because there are multiple nodes across the globe, and they're well-known addresses, and they're all hard-coded in the code base. So Graphene had none of those, and in the initial phase, we didn't want to invest time to implementing other solutions, and for example, using console and console template, which we use in our projects. So we went with the simplest possible solution. So just using NLB for all of the things, for API and for peer-to-peer traffic also. So it's very simple, but essentially it solved the problem. And we just provided well-known NLB endpoint in the configuration file. And for blockchain data, so yeah, we use the EFS. And people asked us, so are you crazy? It's NFS, like come on, right? But we had pretty good results, and initially we just stored everything on the EFS. So when we bootstrap Graphene cluster, so it's ECS cluster running as ISGA, and then we create that cluster-specific EFS volume, which is mounted to all of the nodes, and each node can access the same data. And it was very convenient because any witness instance can start on any of the nodes and can use the data. And at first we stored blockchain data and wallet service and Genesis block configuration, which is I think you need to bootstrap your network. So on EFS volume, and later we moved to EBS volume due to various reasons. At least for storing blockchain data, and common configuration was stored on the EFS. And one thing you need to be aware of, so performance of EFS. So you need to be aware of burst tokens and the performance in general. So if you just create a EFS volume and expect great performance, like just after creating, so it's not going to happen. So you need to write a bit of data before getting decent performance. And for storing the secrets, we use KMS service. So we essentially just use specific KMS key for a cluster, and every cluster has its own key. And we had a custom wrapper which would then use that key to decrypt values in configuration file. So every witness node has its own configuration file, and we left various configuration parameters inside the file untouched, but we encrypted sensitive data. So for example, private and public keys in VAF format. And then the wrapper on the startup of the node, it would, if it has access, required permissions to access Chemia's key, it would then decrypt and output you an encrypted file, which is then stored inside the container, and it's not accessible on EFS, for example. And there was a bunch of other tools and services, and I'll mention a couple of them. So one of them is a CLI wallet service, which is like a wallet server. And this is the a service or interface which you use to integrate other applications which connects to a blockchain. And one interesting thing is that CLI wallet works in the following way. It connects to the backend, so it connects to any of the witness nodes, and then persists that connection. But if that node goes away, it stops working. So we solve this issue by using load balance endpoints in both ways. So applications would connect to CLI wallet using load balance connection, and then CLI wallet itself would connect to the cluster via load balancer. And if you lose the connection, so health check would fail, and then you would automatically restart it. And then again, you establish a connection, and you're good to go. And there is a screenshot of Graphene UI. It's a bit obsolete project, but it's still good to have. It's like looking glass service to have a quick glance how your network is behaving. And it's not so good for like active monitoring, but having this on TV dashboard is pretty nice to have. And we also use the BTS tools, which is open source project, and the author claimed that it supports all of the Graphene forks, including BitShares, Muse and Steemit, and all the others. And that project was abandoned in 2017, if I remember correctly. So, and the problem was that original Graphene wasn't that well supported. So we needed to make some changes, and we usually use that to implement snapshot functionality, and we'll see why it's important. And so this sounds like pretty standard stuff, and we could bootstrap a Graphene network pretty quickly. The whole underlying infrastructure, and everything worked. But as probably most of us learn things while doing them, and we learned few things while running stuff in production environment, in test environments, and later in production environment. And immediately it wasn't apparent, and it took us a bit of time to learn the problems of this project. And so issues we faced with were so at first we didn't notice it until we had decent monitoring in place. So if you leave Graphene nodes just running for a week or so, you don't need to produce any kind of transactions. So all of these nodes would leak memory, and then it would be killed by Linux kernel, and then it restart. And due to a bug in the code base, usually, so when you restart without flushing the state, you would get dirty database. And it is okay because you can recover from that phase. But we faced with a bug, and essentially it would lead to a loop. So when your instance is killed due to out of the memory condition, it would restart, and then it would corrupt the data directory. And you need to wipe it out and start it fresh. And everything's fine when you don't have any data. So catch up is really quick. But if you have any data, so you need to wait until the node catches up. And so that's why we started doing snapshots. So it's really convenient way to catch up. And The only thing which is important, so we found it also the hard way, that when you're doing snapshots and you are assuming that, well, when I need it, right, so I'll just restore from it and let the node to catch up. So the problem was that we didn't test the restore procedure, essentially. So, and we also faced with the issue that sometimes snapshots wouldn't be created correctly, so you would get corrupted snapshot also, and so that was kind of fun bug to deal with. And also one of my favorites was stuck witness process, where they would just stop producing blocks or interacting with other nodes, and without apparent reason. And most of these issues initially were, we just shrugged a lot. And so the initial thought was that most likely it's EFS, right? It should be, like it's NFS underneath, so it must be. But after tracing witness node processes and then after some testing, we moved to EBS volumes and we reproduced the same problems on the cluster. And the same thing happens if you run that on your local node. So if you have dev environment, so we could easily reproduce with a bit of different parameters. And after some time, we found other people who were also test driving graphene as a possible solution. And one company used this exact version of graphene, the original one by Cryptonomics, and another one they were using BitShares, I think so. So they mentioned the same issues, and essentially it's most of the issues are related to the threads locking up, and after that many different things happen. For example, if you kill the node without syncing the state, you get a corrupted database, and as inconvenient it might sound, we fixed most of our problems with this particular piece of software with a ultimate fix, as we call it. So we just we configured our cluster to restart the nodes one by one. So essentially we just used a feature of ECS service. So you just trigger a deploy, and with correct configuration it would restart nodes one by one. And it kind of fixed the problem. It might sound a bit irrational and a bit maybe funny, but it works. And I guess one lesson is when you're designing any kind of system which runs in dynamic environments, you should be aware that your software might not be stopped, for example, in nice ways, and you should be able to recover quickly. And we found out another issue. So at first, when we started doing that, it helped a bit, to manage the memory pressure on the nodes. But another problem was that we would still get corrupted database, and the problem was that ECS scheduler wouldn't wait until witness node finish syncing to the disk. So, and as we were running our custom entry point script, which handles encryption, and after that spawns witness node. So you need to catch signals and then pass them to the node. And or if you're running, I think most of us runs various software in Docker containers nowadays, and especially in cloud. So if you run things on ECS, so make sure that your process is running as an entry point, or make sure that your wrapper can handle signals, because otherwise your SIG term, which is sent to the process, is never get. It never gets that signal. And so when we fixed that problem, so there were still issues with stuck processes, but when you start restarting your instances, so you start using other mechanisms. So that's when we streamlined snapshotting mechanism, which allowed us to more quickly restore the state of the system and then improve our monitoring a bit. And I guess there are two things which are important when running that kind of software or any kind of software in cloud environments. And so it's you need to have decent monitoring and logging if it's available, and also you need to have tools which will allow you to analyze issues in production environment directly, because in our case, so this Graphene project is kind of abandoned nowadays, and we found lots of issues in the code base. And the problem is that we could fix them, at least some of them, but it means that we need to fork the project and maintain it by ourselves. Otherwise, there is no one who can merge your pull request. So for monitoring part, we used CloudWatch for pretty much all the things. And I think it's important that while it's easy to use, so you get only 1 minute granularity metrics, but it's at least something. And also you don't have anything else for like RDS, EB, I don't know, ILB and that kind of services. So you get at least something. And also we run node level monitoring agents, which were sampling state every second. And then it is important to have a monitoring system which can pull all of the sources together, and then you could correlate issues. And that's how we investigated issues related to EFS performance and, for example, IOPS limits when using EBS volumes. And one of the things is, which is, I guess it's very important to monitor burst credits. If that particular service uses that, so for example, EFS uses that, T2 instances, or T3, also uses that. And so when you are dealing with performance issues and you cannot explain them, so these are the first things you should be aware of and check them. And also you should alert on the symptoms at the top level. So you shouldn't be alerting on CPU usage, for example, or on CPU steal time. It's okay to check the hypothesis, but you're going to have a bad time at 3 a.m. because something misfires. And so we derived some metrics and usually alerted on missed blocks metrics, for example, or on production time deviations. And as part of for the logging, I guess it's really important to have a. So we ship all logs from all of the instances to a central logging service. And it's extremely important to have some kind of rate limiting, because if you cannot configure your software to behave in specific ways, you're also going to have a bad time, because two things might happen. So you might DDoS your central service, or with Graphene we had another issue. It would start buffering its output, and you would get no logs for like 1 minute or so, and usually you don't know why it's happening. So yeah, and for debugging, so we use SysDig pretty much everywhere. It's baked in our images. It's not on by default, and it's SysDig is like strace, but on steroids, I would say, and it allows you to trace interaction of programs between kernel space and user space, and it helped us really immensely to identify at least some of the problems with Graphene software. And so we did run this network for a while. But essentially, with all of these issues, we started looking for alternatives. And essentially, it's well, the future path is quite clear. So we are investigating the EOS distribution. So it's the same graphene, but better. So the same author now is working on this project. Hopefully he won't abandon it after 2 years, but they've got so much money now, so that problem probably solved. And yeah, so there are changes in the API, and but it's still less effort than migrating to something else, I guess. And also, so some problems we could repeat some problems like locking up nodes, but at least you can send pull requests to someone and then speak with someone. And yeah, and so the future is looking bright or brighter. And that's it from me.
Thank you, Povilas. I'll be honest, not all of the technical details were clear for me, but because I've seen that, yeah, most definitely you're really deep into this. Any questions from your side? No. I guess something similar to that. I know that you have been doing a lot of projects both on-prem, on public clouds, like for blockchain specifically. If you would like, it would be your choice doing that on AWS or on some on-premises servers and infrastructure. Which would you choose and why?
Well, the answer is it depends, right? Because well, there are it really depends on what you're running, and as Lucas mentioned before, with AWS or any other public cloud provider, you need to be aware of billing issues and resource usage issues. So one of the things we recommend and set up for our customers is billing alerting. So it helped a lot of times, and sometimes you can notice some strange patterns in the infrastructure when analyzing detailed billing statements, because for some reason suddenly your service started hitting KMS service, and that's why you're being billed. And if you're not aware of that, so you need to be you need to have a decent capacity planning process, and it doesn't really matter where you run. And with Amazon or Google Cloud, it doesn't really matter. So you need to be aware if you leave it, especially if you still don't know your baseline performance characteristics and how does the software behaves. So it's extremely important, and it's usually we always start with the cloud usually, unless there are specific requirements to run on premises for some reason, like legal regulation or some other. So and then you migrate or do something else.
Okay, thank you. And have you tried personally some of the new managed blockchain services from AWS?
No, not yet. But well, if it would be possible to drop in, so the managed blockchain service allows you to run like a hyperledger, right? So it's pretty cool. I don't need to do work anymore, right? Yeah. And Ethereum network, so you can do that also. And if you could, like with blockchain templates, so I'm kind of interested, how this thing will progress in the future. So because if you could like provide your own templates, for example, so I would love to, to bootstrap like graphene or other supported things. So the problem with some of the projects are that they were never intended to be run in cloud environments, as we usually see, because you need to add lots of effort to make it operable.
Okay, thank you very much.
Thank you.
Applause to Povilas.